In the middle of the mighty Yangtze River, a massive steel structure stretches from one bank to the other like a straight line cutting across the horizon. This is the Yanji Suspension Bridge, a symbol of China's ambition to conquer its great rivers at the end of the 20th century. With a main span stretching an incredible 1,860 meters, it became the first bridge to cross the 1-kilometer milestone using a single suspended span. But to keep an enormous bridge deck hanging between two towering structures above deep water, engineers had to overcome a series of extraordinary challenges, from complex geological conditions and massive anchor blocks capable of resisting immense forces to installing the main suspension cables and lifting individual steel deck sections high into the air with almost absolute precision. In this video, join Mandarin Tech as we explore how Chinese engineers built a structure that once marked a major turning point in suspension bridge engineering. The Yanji Bridge is located in Hubei Province, central China. In the late 1990s, it was one of the largest infrastructure projects in the country, with a total investment of more than 3.3 billion yuan, equivalent to over 400 million US dollars. The bridge was scheduled for completion in time to commemorate the 50th anniversary of the founding of the People's Republic of China. This turned Yanji into a race against engineering challenges, time, and sheer scale. At the construction site, two bridge towers rising nearly 200 meters had to be built along the banks of one of Asia's largest rivers. Tens of thousands of steel wires were bundled together to form enormous main cables capable of supporting the entire bridge deck above a constantly active shipping route. Meanwhile, the massive anchor blocks at both ends had to absorb the tremendous pulling forces transferred from the cable system into the ground. To make all of these enormous components work together as a single system, Zhongyan demanded a level of precision that China had never before attempted on an infrastructure project of this scale. When construction began, Yanji had not yet taken shape as towering bridge towers or massive cables stretching across the Yangtze River. At the locations of the two main towers, engineers first constructed a specially designed system of board pile foundations. The top and bottom sections of each pile were widened, while the middle section was made narrower. This increased the load transfer area where it mattered most and made better use of the bearing capacity of the geological layers beneath the riverbed. Each borehole had to penetrate deep through layers of sediment before being cleaned, reinforced with a steel cage, and filled with concrete, creating foundations strong enough to support the enormous loads above. From these newly completed foundations, the two bridge towers gradually began to rise above the Yangtze. Steel was connected, formwork was lifted, concrete climbed higher with each construction cycle, until the towers became two enormous landmarks visible from far away on both sides of the river. But Yanji presented an unusual engineering paradox. Because of design limitations, the bridge towers had to be 60 meters lower than the height normally required for a suspension bridge of this scale. As a result, the northern tower was designed with an octagonal outer section and a circular inner section, creating an extremely thick concrete shell around a hollow core. Beneath the river were the foundation piles, locking the enormous loads deep into the ground. Above them stood two massive concrete structures with walls several meters thick, rising into the sky and ready to receive the immense forces generated by the bridge's giant cable system. Suspension bridges are naturally relatively flexible structures. Their main cables run from an anchorage on one side of the river, pass over the top of a tower, stretch across the river, continue over the opposite tower, and finally terminate at the anchorage on the other bank. These two enormous cables become the primary structural elements carrying most of the load from the bridge deck. At the factory, high-strength steel wires are manufactured to uniform dimensions, then arranged in parallel and tightly bundled into groups with an almost hexagonal cross-section. This honeycomb-like arrangement allows the wires to fit closely together, minimizing empty space and creating an extremely dense and compact cable bundle. Once delivered to the construction site, the cable bundles are gradually tensioned between the two towers. The tension must be controlled with extraordinary precision so that the load is distributed evenly among the steel wires, transferred through the main cables to the towers, and ultimately carried into the massive concrete anchorages buried deep within both riverbanks. Once the curve of the main cables has been accurately established and stabilized, a series of vertical suspender cables are installed below. Each suspender is connected to the main cable above and attached to the steel deck structure below. From this point, the weight of the bridge deck is no longer transferred directly to the towers. Instead, it is divided among the individual suspenders, carried upward into the main cables, and then distributed toward the two towers and massive anchorages. Together, this network of main cables and vertical suspenders forms an enormous load-bearing system, allowing tens of thousands of tons of steel in the bridge deck to remain suspended safely and steadily above the river. Once the main cables and suspenders were ready, the construction team moved on to one of the most demanding stages of the project, lifting enormous steel girder sections over the river to form the bridge deck. The prefabricated structural sections were transported by barge directly beneath their installation positions. Above them, a cable crane system running along the supporting cables lowered its hooks, secured each girder section, and slowly lifted it from the deck of the barge. One by one, steel sections weighing more tens of tons were raised high above the water, rotated into the correct orientation, and connected to the waiting suspenders. In this way, the bridge deck, stretching more than 860 meters, gradually took shape section by section above the river. As more steel girder sections were lifted and installed from both sides, the gap over the center of the Yangtze grew smaller and smaller. The two halves of the bridge, each extending for hundreds of meters, eventually stood just one central section apart. The final girder section was transported into position below by barge. The cable crane system then slowly lifted the massive steel structure above the water and carefully guided it into the remaining gap between the two halves of the bridge. The connection points were precisely aligned, secured, and locked into place, transforming two separate structures into one continuous girder spanning the river. From this point, the weight of the bridge deck could be distributed evenly through the suspender system, transferred upward into the four main cables, carried through the two bridge towers, and finally directed into the enormous anchorages at both ends. After years of construction, the foundations buried deep beneath the river, the two towering concrete structures, the four main cables, and thousands of tons of steel girders, had finally become a single structure stretching across the Yangtze River. Before thousands of vehicles could actually begin crossing the bridge, a series of highly precise construction tasks still had to be completed across both levels of the deck. One of the most important was installing the roadway surface above the steel girder structure. Yanji uses a multi-layer pavement system consisting of a waterproof bonding layer, mastic asphalt, and a highly elastic modified asphalt surface. The total area to be completed across both levels reached approximately 130,000 square meters, making it one of the largest single-steel bridge deck paving projects in the middle and upper reaches of the Yangtze River. Alongside the roadway, crews installed a series of less visible systems that were essential to the bridge's actual operation, including safety barriers, drainage systems, lighting, road signs, and traffic control infrastructure. Engineers also had to inspect the entire structure again after the final permanent loads had been added. The elevation of the bridge deck, tension in the 1-4 main cables, condition of the suspenders, and displacement of the 1-2 towers all had to remain within their specified design limits. For a flexible structure of this scale, even temperature and wind conditions at the time of measurement could affect the shape of the bridge. After all auxiliary systems were completed, Yanji underwent further inspection and final acceptance before officially opening to traffic. The bridge was transformed from an engineering project into an important transportation link between Ezhou and Huanggang. But when the first vehicles began crossing Yanji, the challenge for the bridge was far from over. From that moment on, the 4 main cables, on 2 towers, and the entire steel structure, stretching nearly 2 kilometers, would have to continuously withstand traffic, changing temperatures, wind, and millions of repeated load cycles over the decades to come. Based on length alone, Yanji already ranks among the largest suspension bridges in the world, but what sits above that enormous span is what truly makes the structure different. Instead of the conventional two-main cable configuration, Yanji uses four main cables to support a double-deck bridge structure. The upper level carries our 6 expressway lanes, while the lower level accommodates 4 urban traffic lanes. This entire mass of steel had to be stabilized by a load-bearing system that had never before been implemented on a comparable scale. The reason begins with a limitation that might seem completely unrelated to bridge construction. Yanji is located near Ezhou Huahu International Airport, so the height of its bridge towers was strictly restricted. What makes Yanji even more remarkable is how engineers were forced to redesign almost the entire structural system of a suspension bridge to accommodate a limitation that simply could not be changed. The result was a series of engineering trade-offs. The span had to be long enough to keep the shipping channel clear. The towers had to remain low enough to avoid interfering with aviation operations. The deck had to be large enough to accommodate 2 levels of traffic, while the entire structure still had to remain stiff enough to withstand wind and heavy loads. It was this conflict between requirements that seemed almost impossible to satisfy at the same time that ultimately shaped Yanji's unusual design. These features became the engineering solution to a problem that conventional suspension bridge designs would have struggled to solve efficiently at such an enormous scale. For a conventional bridge, engineers can often rely on periodic measurements to evaluate the condition of the structure, but Yanji is different, with 4 main cables featuring different sag profiles, supporting a double-deck steel girder system stretching nearly 2 kilometers. From the construction stage itself, a digital management system was introduced to monitor the bridge almost in real time. A BIM model recreates critical components such as the bridge towers, anchorages, and individual girder sections in 3-dimensional space. Design information, construction progress, and on-site conditions are directly linked to the model, transforming the physical bridge into a digital version that engineers can inspect on a screen. During cable installation, machinery and sensors continuously monitor the shape of each steel wire bundle, its pulling position, and the operating condition of the equipment. Machine vision technology is used to help control the curvature of the cables, while a separate inspection system can detect damage to steel wires during construction. A structure of this enormous scale is no longer managed simply through concrete, steel, and engineering drawings. It is gradually becoming a physical system surrounded by data. And as bridge dimensions move ever closer to the limits of what materials can achieve, the ability to see what is happening inside the structure can sometimes become just as important as making it strong enough in the first place. To understand why Yanji requires as many as 4 main cables, we first need to look at how a suspension bridge stays suspended high above the ground. In this type of structure, the bridge deck is not directly supported from below. Instead, the weight of the deck girders and vehicles is transferred upward through a series of vertical suspenders to the enormous main cables above. These cables pass over the tops of the 2 towers and extend toward massive concrete anchorages at both ends of the bridge. In this way, the load is distributed from the deck into the cable system, through the towers, and ultimately into the ground. Most of the world's famous suspension bridges, such as the Akashi Kaikyo Bridge, are based on a fundamental configuration of 2 main cables, one on each side of the deck. Each main cable measures about 1.12 meters in diameter and is made from tens of thousands of high-strength steel wires arranged in parallel. To form these enormous steel cables, individual wires must be carried across the span, gathered into bundles, carefully aligned, and then compressed into a single unified cross-section. Once completed, they become the massive steel tendons that carry most of the tensile forces generated by the entire bridge. But Yanji takes a different approach. Instead of the conventional 2-cable configuration, engineers designed 4 main cables with different curves, working together to share the immense load of a massive double-deck bridge structure. The significance of Yanji does not end with the moment the 2 banks of the Yangtze River are finally connected. Once it enters operation, the bridge will become a new link in the regional transportation network. Journeys that previously depended on other river crossings can be shortened, while the bridge will also create an additional transportation corridor for people and goods moving throughout the surrounding urban cluster. With a main span stretching more than Yanji, 1 kilometer, it's a double-deck roadway and a system of washed 4 main cables with different sag profiles. Yanji has become a large-scale test of China's ability to design, manufacture, and construct advanced suspension bridges. The technologies used here for cable control, girder lifting, structural modeling, and engineering monitoring could provide valuable experience for even more complex river and sea crossing projects in the future. From a broader perspective, Yanji reflects how China's infrastructure is evolving. Projects are increasingly being integrated into much larger networks, where a single bridge can simultaneously serve urban transportation, expressways, airports, logistics, and the long-term development strategy of an entire region. From the enormous foundations along the banks of the Yangtze River, Yanji shows that modern suspension bridge engineering is not simply a race for greater length. Behind the structure lies a series of seemingly conflicting constraints. The shipping channel had to remain clear, while the bridge itself still had to be large enough to carry both expressway and urban traffic. So what do you think? Is Yanji an engineering marvel, or proof that the toughest limitations can sometimes inspire the boldest designs? Share your thoughts in the comments below. And don't forget to subscribe to Mandarin Tech, so you won't miss our upcoming videos exploring technology and some of the world's most impressive mega projects.